Hi, I'm Shivi and I will be presenting my survey on detecting artificially generated images. This survey is part of my submission for the Electrical Engineering 433 Statistical Pattern Recognition class at Northwestern University. So here's a summary of how this literature survey works. The survey first begins by surveying the introduction to generative adversarial networks. It begins by the emergence of GANs in 2014 and then going forward with the GAN diversification up to 2024, where we stand with OpenAI Sora being one of the most pivotal softwares in generating videos and images from text. The survey then goes in to look at the evolution of artificial imagery all the way from the GANs in 2014 to the Deep Dream and the neural styles developed by NVIDIA throughout the DALI and Midjourney and Stable Diffusion softwares, and emphasizing the rapid technological process and implementation for creativity and security. The survey then goes in to look at the historical context of image manipulation. While image generation as a process has existed beyond 2014, image manipulation has existed from the very beginning of the generation of cameras itself. It therefore goes in to look at the digital age revolutionization by Photoshop, and then looking at the growing sophistication in image manipulation tools. This survey then goes in to look at the advancements in detecting artificial imagery by categorizing them into feature and forensic based methods. The survey covers the evolution from foundational techniques of AI driven approaches, underscoring the complexity and importance of distinguishing between genuine and artificially generated images. The implications for authenticity, ethics, and future trajectories where this presentation comes to a conclusion. Starting with feature-based detection methods. So feature-based detection methods analyze the characteristics and attributes to distinguish real from fake content. They leverage statistical, textual, and visual features to identify discrepancies between AI-generated images. Ideally, this can be performed either through texture analysis, which utilizes distinct textual properties to quantify patterns and irregularities, or through color analysis, where you can look at color histograms and color space analysis to examine graphical distribution of pixel values, or go beyond RGB to analyze images at other spaces like HSV or LAB. We can look at shape analysis, which focuses on edge detection, analyzing the contours and the geometric description of these images. Ideally, AI generated images would exhibit overly sharp or blurred lines. They would have curves outlining objects while detecting unsmoothness or jaggedness. You can look at frequency analysis in the form of Fourier transform, which converts images into a frequency domain, allowing examination of the frequency components and identifying for any anomalies which ideally would not exist in a real world image. Or you can look at wavelet transform, which analyzes the localized area frequency content at different scales, pinpointing specific features or anomalies. Lastly, the spectral analysis, which focuses on the distribution of energy across various frequencies using tools like the power spectral density, which typically shows smoother textures and reduced power in higher frequency bands. Now, what are some forensic based methods? Forensic based methods will utilize digital forensic principles to detect signs of manipulation of artificial generation, which basically focuses on analyzing artifacts, inconsistencies, and anomalies introduced by AI generation softwares. When looking at compression artifact analysis, it focuses on detecting anomalies introduced by image compression. When looking at noise pattern analysis, it examines the unique noise characteristics inherent to digital images. This also includes GAN fingerprints. Lighting and shadow analysis focuses on the consistency and physical plausibility of lighting and shadows within an image. Discrepancies in these elements can indicate artificial generation. Geometry and perspective analysis criticizes the geometric consistency of perspective accuracy. Natural images adhere to perspective laws and geometric coherence, focusing on the laws of physics. Since the evolution and the invention of GANs in 2014, generative adversarial networks have, in general, various datasets which help improve their overall generational accuracy. Along with this inclusion, there has also come a new challenge where it's important to detect such generated images as they pose harm and can attack government systems, social media platforms, etc. Therefore, there are various common data sets which are state of the art when it comes to detecting artificially generated images. Face Forensics Plus Plus is a step up from the face forensics dataset. It is a comprehensive dataset of video sequences manipulated from 4 different sources and is designed to challenge detection models. It showcases a proposed architecture for detecting real and fake images using convolutional neural networks and also provides its own dataset. The deepfake detection challenge was introduced by Facebook, now known as Meta, and is among one of the largest collection of deepfake videos with over 124,000 videos. It aims to advance the overall development of detection mechanism by providing a diverse set of manipulated content, but can also be used for detecting artificially generated content. The Celeb DF is a focus is on high quality celebrity video clips to improve the realism of deepfake videos. The Celeb DF addresses common issues in earlier datasets such as visible artifacts and inconsistencies, making it significant in deepfake detection algorithms. GAN generated datasets such as StyleGAN 2 and Big GAN have been introduced by NVIDIA. They comprise of a wide range of subjects from human faces to natural scenes produced by advanced GAN frameworks. These advanced datasets challenges the detection models with the high quality and diversity, pushing them to the limit of distinguishing between real and AI generated content, ensuring that they can be generalized across various system to system and algorithm to algorithm and dataset to dataset. This person does not exist is not a traditional benchmark dataset, but it does offer a collection of photorealistic images generated by StyleGAN2 and serves as a resource for understanding and detecting AI generated faces. The CASIA image tampering detection evaluation database originally focused on traditional image tampering. The CASIA dataset now also supports the development of unique techniques for detecting AI generated images. It provides a mix of manipulated and original photos for comprehensive algorithm training and evaluation. The main goal of this literature survey is to review the various feature and forensic based methods that are currently available and are the state of the art when it comes to detecting artificially generated images. The error level analysis and a photo response network unit utilizes pixel wise feature extraction techniques in conjunction with CNNs, therefore achieving over 95% accuracy in identifying AI created images. The PRNU identifies serious sensor noise patterns which are unique to camera images, while ELA focuses on JPEG quantization errors. JPEG Ghost introduces a method to detect forgeries in JPEG images by identifying inconsistencies in JPEG compression. This utilizes a structural similarity index measure which predicts the JPEG quality to localize tampered areas effectively, proving robust across various scenarios. Lighting analysis employs the color constancy technique to extract lighting information, enhancing the detection accuracy. Has been tested across multiple datasets. This model significantly improves the deepfake detection, especially in low quality videos by incorporating semantic lighting information. Clone detection is a method which advances the detection of copy move forgeries using GAN, that is therefore one of the most earliest methods for detecting forgeries and manipulations in forensic detection. It requires only genuine and forged samples for training and is therefore quite efficient. It simplifies the detection process and outperforms traditional feature extraction based methods in forgery detection. Chroma subsampling introduces the detection of chroma wrinkle artifacts from chroma subsampling in the JPEG compression. These artifacts, detectable with high accuracy, aid in determining the JPEG compression library used, enhancing image authentication and origin determination. When it comes to JPEG compression, this process is quite useful and is a state of the art when implemented in the SMPs, which are your social media platforms, and can therefore work on mobile devices. Local binary pattern histogram analysis is a method that combines YOLO for face detection with LBP for temporal and spectral features. It demonstrates high precision and recall rates across various datasets and outperforms existing deepfake detection software, emphasizing the importance of integrating spatial and temporal features to the overall detection methodology. Frequency analysis investigates GAN generated images through the frequency analysis, identifying unique artifacts consistent across different GAN architectures. This approach offers better robustness against common image perturbations and enhances the detection efficiently. The geometric consistency leverages the consistency of facial geometry across multiple video angles to detect deepfakes, focusing on mouth movements so that the system is not generalized just to the front face of the feature. It uses PCA and hierarchical clustering. It identifies manipulated videos, promising a new tool for collaborative video verification. Texture analysis develops the LBP net using the local binary pattern to detect texture inconsistencies in facial images. It demonstrates high detection accuracies across various datasets. LBP net shows great potential in deepfake detection under different conditions. The CFA analysis enhances the deepfake detection using bilateral high-pass filters, which focus on frequency level artifacts uncommon in deepfake images. This method significantly outperforms existing techniques, providing a generalized approach to artifact detection. Morphing detection proposes a detection method for deep morphed images tailored for IoT devices with high accuracy, making it suitable for smart city applications. It ensures that the security and reliability of facial recognition system it works against deepfake threats and is therefore quite useful when it comes to government-based softwares and systems. GAN fingerprints identifies the attributes of GAN generated images through unique fingerprints. GAN fingerprints is basically a forensic method where it is noted that generative adversarial network systems would ideally leave behind a certain pattern, sort of in the format of fingerprints, which can be used for classifying these images. This method is robust to perturbations and sets a new standard for image attribution for digital image forensics. These were a general few algorithms which are quite useful when it comes to forensic formats of detecting generative adversarial networks. There are also various other algorithms, but these are the current state of the art in the field. Now, what are some feature-based methods which can help improve the GAN detection process? Edges and optical flow incorporate edge maps and dense optical flow maps with exception net architecture, which enhances the detection across various video formats and compression levels. This approach achieves remarkable accuracy and robustness, setting new benchmarks in deepfake detection. The histogram of oriented gradient descents, the HOG, utilizes HOG for feature extraction and SPM for classification, efficiently detecting face-to-face manipulations in videos. This method highlights visual discrepancies and synthetic faces, proving effective under varying compression qualities. The SIFT and the SURF introduce FFRFD, which combines these methods to detect feature point defects in the facial region, indicating fewer feature points in deepfake faces. This lightweight approach offers efficient and accurate detection across multiple datasets. Co-occurrence matrices employ cross-color spatial co-occurrence matrices integrated with a DNN, a deep neural network, for fake image detection. This model outperforms existing methods because it has strong generalization capabilities in diverse conditions and can therefore be used from model to model. When it comes to cardboard filters, it integrates adaptive cardboard filters with a CNN to improve deepfake detection. This model significantly reduces size without sacrificing the performance, demonstrating superiority across benchmark datasets. Siamese networks, as proposed in LICE-SIAM, a Siamese network enhancing robustness against image degradation through localization invariances. This network shows superior performance in detecting manipulated regions and outperforms existing models in cross-database evaluation. It is therefore a very generalized software and can work across model to model and image to image. ExceptionNet adapts the exception network to process images in the YCBCR color space as opposed to the RGB color space and significantly improves the deepfake detection accuracy. This method addresses the misinformation and legal challenges posed by deepfake images quite effectively. It is therefore a state of the art in the field. Feature Fusion introduces MFFNet, which combines RGB, textual, and feature frequency for deepfake detection. This framework's novel diversity, loss function, and feature fusion strategy enhance the accuracy and generalization, showcasing robustness against disturbances and can therefore handle noises quite effectively. The literature survey also goes on to evaluate the various benchmark datasets that have tested the state of the art algorithms against some of the most common deepfake detection datasets. So, Deepfake Bench is one such benchmark test which evaluates 15 detectors across their native, spatial, and frequency categories. The native detectors use a CNN architecture directly, the spatial detectors use CNN with manual algorithms, and frequency exploit the frequency domain information for deepfake detection, therefore covering a vast space of the overall detection methodologies. Now, naive detector performance highlights the key naive detectors like MESO4, the MESO-inception, and exception, with exceptions show impressive average scores across various datasets. The spatial detectors show like the FWA, the face X-ray, and the UCF incorporate manual design algorithms with CNN backbones, and they demonstrate high performance with UCF, achieving notable average AUC scores in the domain-specific evaluation. Frequency detectors such as the F3net and the SRM focus on frequency artifacts, with the F3net achieving high average scores, indicating the efficacy of frequency analysis. When it comes to the within domain evaluation, the assessments have detectors exhibit commendable performance with high AUC scores. With cross domain evaluation, the detectors like SPL and SRM show robust performance, indicating good generalization in general across various datasets. Another such benchmark is the Auto 2020, which has facilitated a comparison of various deepfake detection models, indicating that the models are fine-tuned on specific datasets tend to perform better. The research includes a detailed benchmarking process and outcomes for different deepfake datasets. They discuss the effectiveness of deepfake accuracy techniques based on the accuracy, the log weighted precision, and a recall rate. Efficient, a DFDC, and the six method ensemble network showcase strong performance across the different datasets. This brings my literature survey to a conclusion. So, as we can see, this literature survey has successfully managed to provide a diverse, comprehensive view of the various feature and forensic based methods when it comes to detecting deepfake images, AI generated images, while also evaluating the various benchmark tests that have been performed and are available to the general public. Thank you.